In this lecture, we're going to look in more detail at reactions of epoxides to try to break down what's happening in terms of which side is being attacked, what's the stereochemical outcome, and then how do you tell if you have reactions that are under acidic or basic conditions. So I believe, get back to the right page here. Sorry, should have had this done. Get back to lecture titles. This is lecture 21. So let's go into the reactions under basic conditions. So reactions of epoxides under basic conditions. Now, the first thing I want to address is what's the nucleophile? So for this class, there's going to be two possibilities. They serve as good reminders of the previous section, along with good opportunities to discuss review of things like the Grignard reaction. So I'm going to show two examples here. These are just two examples of classes of molecules. The first one is an alkoxide, and the second one is a Grignard reagent. Now, the alkoxide is typically countered by Na+, but what you're going to see is RO and then some metal. And these are things we looked at in the Williamson ether synthesis in the previous few lectures. But the Grignard reagent, this is R attached to MgBr. In this case, R is a butyl group, and in other cases, R could be just other things. So let's look at this. These are going to be our two nucleophiles. That is to say, if I take an epoxide, and I really like this epoxide for the time being, and I react this with our alkoxide, and I ask the question, what's the outcome of the reaction? The first thing I want to do is cross out the Na and put a negative charge. This is a strategy we talked about. Now, the negative charge is going to then engage the epoxide at the delta positive on the less substituted position. It could be the left or it could be the right. I tend to stick with this example as we're first looking at these reactions. So it's going to add to the epoxide side on the right, pushing the electron density up and onto the oxygen atom. That's going to give us an intermediate where the oxygen is on the left and it's negatively charged. Draw a line down to show that the nucleophile has added. Now the nucleophile is kind of facing downwards, and that's going to help us in future lectures when we talk about things like stereochemistry. I'm going to emphasize here, this is the new bond. Now, the thing that I had overlooked in writing this reaction is I have to add a workup step, which I write as then H+. It's telling me I'm not adding H+ at the outset of the reaction, at the beginning of the reaction. Instead, I'm adding it at the end of the reaction to clean up any negative charges that are left over. And you can see we have a negative charge, which will be neutralized by the H+. We'll let the negative add to the positive. That's going to give us a structure that looks like this. And I guess I can just turn this page. I twisted my ethyl group up. I'm going to move it down just so you can kind of hopefully see the connection. We still have our new carbon-oxygen bond. I know that in the last step, that's not a bond that was formed, but I just want to emphasize that's the bond that we should see. Now, sometimes students will lose carbon atoms, so kind of make sure, check your work, count your carbons in the starting materials and the final products. The reason why they do is just from bond line structures. If you don't draw the C's, sometimes you start to lose track of them. And that's especially the case in the next example when we look at the Grignard reagent adding to our epoxide that doesn't have symmetry. So if we take our epoxide that doesn't have symmetry, it's got a non-substituted side and a substituted side. Okay, now I've got a Grignard reagent adding to the epoxide. So I'm going to cross out the magnesium, but I also need to cross out the bond from carbon to magnesium. Maybe I write that C a little bit more explicitly, put a negative charge on it. That'll tell me where that C is so I don't lose track of it. In fact, we have 1, 2, 3, 4 carbons we need to make sure come along for the ride as the negative charge is engaging the delta positive on the less substituted position of the epoxide. We're going to release the ring strain by ring opening the epoxide. What I'm going to do is just sort of let that epoxide tilt over. If you think about it, it's closed up in a ring during the ring opening. We'll break this bond. We're going to let that epoxide oxygen swing open to relieve the ring strain and get back to a tetrahedral geometry. That's going to look like this. So I'm going to have two methyl groups, oxygen with a negative charge. And then going down, this is where it's kind of tricky. I'm going to put some symbols here so I can keep track of this. And this is only tricky because of bond line structures. Okay, so I've highlighted with a dot the carbon atom from the epoxide, which is connected, which is also in the product. I'm going to put a square on the carbon. I probably should have just written a big red C. Maybe I'll still do that. That's carbon 1 of our butyl chain connecting to the epoxide carbon to make the new bond from the epoxide carbon to the Grignard reagent carbon. So this is my new bond. And this is carbon 1, 2, 3, 4. If you want to count them, you can. But hopefully you can see my point that this is a challenge for some people, for everybody, not some people. It's a challenge for me when I was a student. Just learning to count carbons, making sure we don't lose them during the course of the reaction. And just like before, and I probably forgot it in the original reaction, we need to add a then H plus workup step. When that happens, we get to an alcohol product, and I like to have everything sort of drawn with minimal rotations just so I can make sure I didn't lose track of any carbon atoms along the way. Okay, so what I need to do is just go back up and write then H plus so that when I PDF these notes, you can see where the H plus is. Oh, I've got it here. I could just do this, then H plus question mark. Okay. So when we add a nucleophile under basic conditions, what that's saying is we're not necessarily adding a base. Both of these are basic, but that's not what we're getting at. When I say we're under basic conditions, we have a nucleophile that's special enough to react with the epoxide, maybe special is a strong word, that is good enough to react with an epoxide without pre-activating that epoxide with an acid. Okay, so what I want to do now is move into acidic conditions. We're going to get a little bit of a hitch with the acidic conditions. So these are ring opening reactions under acidic conditions. And I again want to start with the question of what's the nucleophile? What's the nucleophile? So the nucleophile is typically often an alcohol. It could be other things. Or I don't think it really works, but you probably could have a halogen atom. Okay, let's look at some examples. So if we have an alcohol, this is what the reaction is going to look like. We'll predict the products here in a second. Now what I'm going to do is I'm going to add an H plus catalyst. Could be any of the, we could have H3PO4 or H2SO4, whatever sort of works better under the reaction conditions and plays well with the reagents. So if you notice, I write cat with a period. So if you put cat without a period, it's a cat. But if you put a cat with a period, it's implying that we're using the H plus as a catalyst, or we're adding a substoichiometric amount, that is a small amount of H3PO4 to donate a small amount of H plus. We don't need a full stoichiometric equivalent, a full molar equivalent, a 1-to-1 ratio of moles. We don't need that for this reaction. Instead, we can just get away with simply using a smaller amount. And we could see that from the mechanism. And the mechanism is also going to allow us to see what the product's going to be. Okay, so what is this mechanism for this reaction? What I'm going to do is just go straight down from the starting materials. and I'm going to write the product, which is a protonated epoxide, after one of the lone pairs has engaged the H+. Here's yet another example of a mechanism where we have a strong acid added at the beginning of the reaction. When we do that, we want to let the single subatomic particle do the reacting first before anything else. So that's going to get to a protonated epoxide. Now these are weird. So what I've been doing so far is drawing the epoxide as sort of an equilateral triangle, right? Because every carbon sort of suffers to the same degree. That works on paper, but in reality, we're going to see some distortion, particularly when the H plus is added to the reaction and we see the protonated epoxide form. So we get enough and sufficient distortion. It's not really a reaction. I'm just going to depict this in a different way. We're going to get to a distorted epoxide. And what a distorted epoxide is going to look like is we're going to widen one of the carbon-oxygen bonds. And in this case, it's going to be on the left side. I'm going to really exaggerate that. That doesn't look good. I really want to be super precise about it, but it's not helpful. So I'm just going to kind of lengthen the left bond and leave the right bond the same. Okay, so that is in response to the formation of a positive charge on the oxygen atom. So what I want to point out is that this bond is longer, and longer bonds are weaker bonds. And if it's a weaker bond, we're going to see this bond to be more reactive, more likely to spring open in the event of a nucleophile becoming nearby. So we're going to have our nucleophile come by. Now our nucleophile is not an O- because we're under acidic conditions. That is, any O- that we formed is going to be neutralized by our acid, even if it's an acid catalyst. We haven't added anything to the reaction to really take that hydrogen away from a neutral alcohol. So it's got to come along for the ride. That's no big deal. So we're going to have the oxygen atom attack. Now it's going to attack this time the left side, or the more substituted position, because the bond is longer and thereby weaker and thereby more reactive. So we're going to attack the left side, which is the more substituted position. And when we do that, we get to a ring opened epoxide, where there's the alcohol oxygen. Here's 2 methyl groups. Okay, we've ring opened the epoxide. No big deal. We're done, right? Just a second. Okay, I said the hydrogen, and in this case, the ethyl group had to come along for the ride. As a result, the oxygen now has a positive formal charge. So the oxygen that did its attacking now is a positive formal charge. We went from a positive formal charge on the epoxide to a positive formal charge on the new oxygen that has been added. How do we handle that? It's no big deal. Many people get screwed up by this, okay, and get kind of lost right here. All we have to do is let that hydrogen walk away as H+. The hydrogen is going to dump its electrons into the oxygen atom. That's going to give rise to a product where we have our OH from our epoxide. Our oxygen still has the ethyl group from ethanol adding. Now 2 lone pairs of electrons, and we've regenerated H+. And if H+ is the starting material and a product of the reaction, it's a catalyst. So we show the H+ as a catalyst of the reaction. Okay. What I want to do now is, I think this is good for, I think we're ready for a break, as we've just seen a lot of mechanisms, but you probably still have a lot of questions. Why did we see the epoxide distort when it was protonated, but not when it wasn't protonated? And why did it distort only to that left side and stretch only that left side bond? We can explain all of that, and we'll do that in the next lecture on regioselectivity and stereo specificity. Okay, so we'll finish this lecture here.